While the world obsesses over 3i Atlas, that distant interstellar wanderer drifting through the outer solar system, something far more immediate is bearing down on us. April 13th, 2029, mark that date. An asteroid named Apophis, the god of chaos, will pass so close to Earth it'll fly beneath our satellites. 30,000 kilometers. That's closer than your GPS signal originates. Scientists say we're safe, but new models suggest the flyby itself could change everything. Tidal forces, surface shifts, tiny orbital nudges that compound over decades. What if that close encounter isn't the end of the story, but the beginning? Stay with me, because what happens in 2029 might determine whether we face a threat we're creating right now by not looking closely enough. If you're as captivated by this as I am, hit subscribe so you don't miss a single part of this story as it develops in real time. Leave a comment telling me where you're watching from, what time it is there, and what you think happens to us in 2029. Are we actually safe or just optimistic? Part 1. The close encounter no one's prepared for. While the world fixates on 3i Atlas, that mysterious interstellar wanderer drifting through the solar system, like some cosmic ghost, something far more immediate is bearing down on us. Something we've known about for decades, something that could change everything in a single afternoon in 2029. Its name is 99,942 Apophis. You might know it by its nickname, the God of Chaos. Fitting, isn't it? Named after the ancient Egyptian deity of darkness and destruction, this chunk of rock, roughly 340 meters across, is going to pass so close to Earth on April 13th, 2029, that it will literally fly beneath some of our satellites. We're talking about 30,000 to 32,000 kilometers from Earth's surface. That's closer than the geostationary belt where your television broadcasts and GPS signals originate. For context, the International Space Station orbits at roughly 400 kilometers. Apophis will be 75 times farther out than that, but still absurdly, terrifyingly close for something so massive. Let me put this in perspective. An asteroid this size passing this close to Earth is essentially unprecedented in recorded human history. We've had smaller objects zip by closer, sure, but something 340 meters across, something capable of unleashing the energy of hundreds of nuclear weapons if it struck us, coming within spitting distance of our satellite infrastructure, that's a once-in-a-millennium event playing out in our lifetime. You can visualize the path. Picture Earth as a blue marble suspended in space, wrapped in concentric rings of satellites. The innermost ring holds low Earth orbit craft, then comes medium Earth orbit with navigation satellites, and finally the geostationary belt, a crowded highway of communication satellites fixed above the equator. Apophis will thread the needle between Earth's atmosphere and that geostationary ring. It will be visible to the naked eye in some parts of the world, a bright point of light moving perceptibly against the background stars. People will gather in the streets to watch, children will point, someone will live stream it. It will trend on social media for exactly one news cycle, and then everyone will move on, assuming the danger has passed. But here's what keeps planetary scientists awake at night. Here's the question that NASA and the European Space Agency are carefully, diplomatically avoiding in their public statements. What if that close approach doesn't just give us a spectacular sky show? What if it fundamentally changes Apophis itself? What if Earth's gravity doesn't just pull the asteroid close, but actually reshapes it, spins it differently, alters its surface, triggers forces that we haven't fully modelled yet? And what if those changes, subtle and invisible to the casual observer, set Apophis on a trajectory that brings it back? The official line is reassuring. NASA has stated clearly that Apophis poses no risk of impact in 2029 or for the next century. The European Space Agency echoes this. The math has been checked and rechecked. The orbital calculations are solid. We're safe. But scratch beneath that surface confidence, and you find something more complicated. You find dynamicists, the scientists who specialize in calculating asteroid orbits, still publishing papers about Apophis, still modeling tiny accelerations, still mapping uncertainties, still asking what-if questions about forces so subtle they're measured in millimeters per second. Why would they do that if the case was closed? Because they know something the public doesn't fully grasp yet. They know that the 2029 flyby isn't the end of the story. It's the beginning. It's the moment when small uncertainties could bloom into catastrophic ones. It's when the margin for error that currently keeps us safe could evaporate entirely. Think of it this way. Right now, Apophis follows a predictable orbit. We've tracked it with radar. We've measured its position against background stars. We've built models of where it will be years and decades into the future. But all those models depend on assumptions. They assume Apophis is a certain mass. They assume its surface reflects light in a certain way. They assume it rotates at a certain rate. They assume no external forces are acting on it beyond simple gravity and momentum. What happens when some of those assumptions turn out to be wrong? What happens when the 2029 flyby introduces variables we didn't account for? What happens when the rock that emerges from that encounter isn't quite the same rock that went in? The answer is that our carefully constructed probability maps, our reassuring century-scale safety projections, could become obsolete overnight. We could be looking at a completely different threat landscape, and we wouldn't necessarily know it immediately. The changes could be subtle enough that it takes months or years of additional observations to realize our models have broken down. This isn't fear-mongering. This is what the cutting-edge research is actually saying, if you read between the lines. Papers are being published right now exploring scenarios where Apophis experiences tidal reshaping during the close approach, where its rotation state changes, where surface material shifts and alters the thermal properties of the rock. Each of these scenarios opens a door to orbital changes we haven't fully mapped yet. So while everyone watches the distant visitor, the interstellar interloper that poses zero threat to us, the real story is unfolding much closer to home. The god of chaos is coming, and when it arrives, we'd better hope we understand it as well as we think we do. Because if we don't, April 13th, 2029 won't be remembered as the day we dodged a bullet. It will be remembered as the day we sealed our fate and didn't even know it. Part 2. The comfortable lie. We're all believing. Let's talk about what NASA actually said. Not what the headlines claimed. Not what your uncle shared on social media. What the agency that monitors these things for a living actually carefully stated about Apophis. In March of 2021, the European Space Agency officially removed Apophis from its risk list. NASA followed suit with similar statements. The key phrase everyone latched onto was that Apophis posed no risk of impact for at least the next century. The Planetary Society, one of the most respected space advocacy organisations in the world, has confirmed this assessment repeatedly. The case was closed. The internet could stop freaking out about 2029 and 2036. We're safe. Except that's not quite the full picture. Because while those statements are technically accurate based on current data and current models, they come with invisible footnotes that nobody reads. Footnotes about confidence intervals, about measurement uncertainties, about physical processes we're still characterizing, about the difference between no measurable risk with current instruments and definitively no risk under any conceivable circumstance. The scientists who study asteroid dynamics haven't stopped working on Apophis. If anything, the research has intensified as 2029 approaches. They're not publishing papers that scream we're all going to die. They're publishing papers with titles like Tidal Resurfacing Model for Apophis and Constraints on Yarkovsky Acceleration and Post-Encounter Orbital Evolution. Academic, technical, easy to ignore if you're not in the field. But read those papers, and a different story emerges. A story about forces so small they barely exist, but so consequential over long timescales that they could rewrite everything. Let me introduce you to the Yarkovsky effect. Imagine an asteroid tumbling through space. The sun heats one side. That side radiates the absorbed heat back into space as infrared light. But the asteroid is rotating, so by the time that heated surface faces away from the sun and releases its energy, the asteroid has turned slightly. The result is a tiny, tiny thrust, like a bottle rocket that fires constantly in one direction. Over years and decades, this imperceptible push can shift an asteroid's orbit measurably. For Apophis, the Yarkovsky effect matters because we don't know exactly how strong it is. We don't know the asteroid's exact thermal inertia, how quickly it heats up and cools down. We don't know its surface roughness in enough detail. We don't know its rotation state well enough. All of these factors feed into the calculation, and all of them carry uncertainties. Now add the 2029 flyby into the mix. When Apophis screams past Earth, our planet's gravity is going to squeeze it. Tidal forces, the same forces that create ocean tides on Earth, will stress the asteroid's structure. The side facing Earth will feel a stronger gravitational pull than the side facing away. For a solid chunk of nickel iron, this might not matter much. But if Apophis is what scientists call a rubble pile, a loosely bound collection of rocks and dust held together by weak gravity and maybe some cohesion, those tidal forces could trigger landslides, could shift surface material, could expose fresh rock with different thermal properties. Change the surface and you change the Yarkovsky effect. Change the Yarkovsky effect and you change the orbit. Change the orbit and suddenly those century-scale safety assurances are based on outdated assumptions. The numbers here are sobering. Orbital dynamicists have shown that a velocity change of just millimeters per second, sustained over years, can translate into positional differences of hundreds or thousands of kilometers down the line. It's like aiming a rifle. A tiny deviation in the barrel's angle becomes a massive miss at long range. Except we're not trying to miss. We're trying to predict where the bullet will be, and we're realizing the barrel might be wobbling in ways we didn't account for. Recent modelling has shown that even 1% of Apophis's surface experiencing change during the flyby could be enough to alter its thermal properties measurably. 1%. That's not some catastrophic reshaping. That's not the asteroid splitting in half. That's a subtle surface modification that you might not even notice with a telescope, but it's enough to matter. There's another complication. Apophis might not be rotating simply. Some models suggest it could be tumbling, rotating around multiple axes simultaneously, like a badly thrown football. If that's true, modelling the Yarkovsky effect becomes exponentially more complex. The heated surface is no longer predictable. The thrust direction varies chaotically. Suddenly your neat orbital projections become probability clouds. And here's where the official statements start to feel less like bedrock certainty and more like educated guesses hedged with caveats. When NASA says, no risk for a century, what they mean is, based on our current best understanding of this object's mass, shape, rotation, surface properties, and orbital dynamics, accounting for known perturbative forces including solar radiation pressure and the Yarkovsky effect, we calculate no significant probability of impact within a 100-year window. That's a very different statement. It's conditional. It's model dependent. It's only as good as the data feeding it. So what happens if the 2029 flyby reveals that some of our assumptions were wrong? What happens if the asteroid emerges rotating differently? What happens if surface changes alter its reflectivity? What happens if the models that assured us we were safe turn out to have been built on incomplete information? We start over. We recalculate. And we hope we have enough time to do something about what we find. Part 3. The models that changed everything. In 2023, a team led by researcher Kim published a paper that sent quiet shockwaves through the planetary defense community. The title was technical and forgettable. The implications were anything but. They had built a detailed model of what would happen to Apophis during the 2029 close encounter. Not just the orbital mechanics, which had been calculated to death already, but the physical changes to the asteroid itself, what the tidal forces would actually do to the rock as it passed through Earth's gravitational field. Their conclusion was startling. Roughly 1% of Apophis's surface might experience what they called resurfacing during the flyby, material movement, grain flow, essentially landslides happening in slow motion as Earth's gravity kneaded the asteroid like dough. 1% doesn't sound like much. It's easy to dismiss. But context matters. That 1% represents potentially millions of tons of material shifting position. Fresh rock exposed, dust redistributed. The asteroid's albedo, its reflectivity, altered in localized patches. And remember what we discussed about the Yarkovsky effect, about how thermal properties control that subtle but crucial thrust. Change the surface and you change everything downstream. The Kim paper did something else important. It opened the door to a cascade of questions that researchers are still grappling with. If tidal forces can trigger surface movement, what else might they trigger? Could they change the asteroid's spin rate? Could they nudge it into a tumbling state? Could they reveal subsurface material with radically different properties? Could they, in extreme scenarios, cause structural damage? Let's walk through the chain of causation here, because this is where tiny changes become huge consequences. Start with the flyby. Earth's gravity squeezes Apophis. Surface material shifts. A patch of darker, less reflective rock gets exposed. That patch absorbs more sunlight and radiates more heat. The Yarkovsky effect in that region strengthens slightly. Over years, that extra thrust accumulates. The asteroid's orbit bends by kilometers, then tens of kilometers, then hundreds. Now project forward to 2036, when Apophis makes another relatively close pass to Earth. Except this time, because its orbit was nudged by that altered Yarkovsky effect, it's not quite where the old models predicted. Maybe it's a few hundred kilometres off. At the scale of the solar system, that's nothing. At the scale of hitting or missing a planet, that's everything. The models show something else troubling. If Apophis does experience significant rotation changes during the flyby, our ability to predict its future Yarkovsky acceleration degrades dramatically. A simply rotating object is predictable. A tumbling object is chaotic. The thermal thrust vector precesses. The orbit becomes harder to calculate precisely. The uncertainty bands widen. This is the part where I need you to understand something fundamental about orbital dynamics. Predicting where an asteroid will be in 5 years is relatively straightforward. Predicting where it will be in 50 years is harder. Predicting where it will be in 100 years requires accounting for every tiny force acting on it over that entire period. Miss a force or miscalculate its magnitude, and your prediction will be wrong. And here's the kicker. The 2029 flyby is, in effect, a giant reset button on our understanding of Apophis. Everything we think we know about its thermal properties, its rotation, its surface characteristics, all of that could change in a matter of hours as it passes Earth. We'll need to remeasure everything afterward, rebuild our models, recalculate the risk. That takes time, and during that time Apophis will be drifting along an orbit we no longer fully understand. Other researchers have picked up this thread and run with it. There are papers now exploring different scenarios. What if the rotation change is more dramatic than Kim's model suggested? What if the surface change is less than 1%, but concentrated in a specific region that maximizes Yarkovsky effects? What if the asteroid's internal structure is weaker than we thought, and the tidal stress causes not just surface changes, but deep structural groaning? Each scenario opens new branches in the probability tree. Each one requires different assumptions and yields different long-term predictions. And crucially, we won't know which scenario is closest to reality until after the flyby happens. This is what I mean when I say the official statements about safety are conditional. They're based on models that assume no significant changes during the encounter. But the cutting-edge research is saying that assumption might not hold. Think about it like this. Imagine you're predicting the path of a train. You know its speed, you know the track layout, you can calculate exactly when it will reach any given station. Now imagine someone tells you that at one point in its journey, the train will pass through a station where workers might possibly adjust the track slightly, not derail it, not stop it, just tweak the alignment by a few degrees. Suddenly your arrival predictions for stations farther down the line become less certain. You need to wait for the train to pass that station, see what actually happened, then recalculate. Apophis is the train, the 2029 flyby is the station, and we're all waiting to see if the tracks get adjusted. The researchers aren't panicking. Science doesn't work that way. They're systematically exploring the parameter space, quantifying uncertainties, publishing their findings in peer-reviewed journals where other experts can scrutinize them. This is how it should work. But it does mean that anyone telling you with absolute certainty that Apophis poses zero threat for the next century is either oversimplifying or hasn't read the latest research. The more accurate statement is that we think we're safe based on current models, but those models have known limitations, and the flyby represents a critical test of whether those limitations matter. We're about to find out. Part 4. When rocks fall apart. There's a scenario that keeps appearing in the technical literature. Nobody wants to talk about it in plain language because it sounds too much like a disaster movie. But it's grounded in real physics and real observations of how asteroids behave under stress. What if Apophis doesn't just change slightly during the flyby? What if something breaks? Not in the Hollywood sense of the asteroid shattering into 1,000 pieces, but in the more subtle, more insidious sense of an object that's barely holding itself together to begin with losing some of that tenuous structural integrity. Let me explain what we mean when we say an asteroid is a rubble pile. Many asteroids aren't solid chunks of rock. They're more like beanbags, collections of smaller rocks, boulders, pebbles and dust, all clumped together by their own weak mutual gravity. Maybe some electrostatic forces, maybe some cohesion from fine dust acting like glue, but fundamentally they're fragile. Laboratory experiments on meteorite samples have shown how little force it takes to initiate landslides or grain flow in this kind of material. Now subject that structure to tidal stress. The near side of Apophis will feel Earth's gravity pulling harder than the far side. That creates a stretching force across the asteroid's diameter. For a solid object, no problem. The material can handle that stress easily. But for a rubble pile, that's a different story. Imagine a bag filled with marbles. If you pull on opposite sides of the bag gently, nothing happens. Pull harder, and the marbles start shifting. Pull hard enough, and some might slip past each other, redistributing themselves, changing the bag's shape. That's what tidal forces could do to Apophis. The Kim tidal resurfacing model suggested this kind of surface material movement is plausible. But what if it goes further? What if subsurface structures shift? What if the asteroid's shape deforms measurably? What if, in a worst-case scenario, a chunk actually separates? This isn't wild speculation. We have precedent. Binary asteroids exist, pairs of rocks orbiting each other, likely formed when a parent body was stressed enough to split. We've observed asteroids that are clearly contact binaries, two lobes barely touching. We know these objects can be structurally complex and vulnerable. If Apophis loses mass during the flyby, everything changes. Your mass estimates are wrong, so your gravity calculations are wrong. Your rotation modelling is wrong because the moment of inertia changed. Your Yarkovsky predictions are wrong because the thermal properties changed. You now have two objects to track instead of one, and the smaller fragment might be on a completely different trajectory. Here's the really troubling part. A small fragment separating from Apophis might not be immediately obvious. If it's a slow separation, a boulder gently drifting away at a few centimetres per second, it could take weeks or months of observation to confirm it happened. During that time, we're tracking what we think is a single object, building models based on that assumption, when the reality is messier. And if that fragment is on a different orbit, if the separation event gave it a slightly different velocity, it could end up hitting Earth even if the main body misses, or vice versa. You've just turned a single probability calculation into a multiple body problem. The analogy here is a snowball rolling downhill. Start with a compact snowball and you can predict its path reasonably well. But if that snowball starts picking up debris, or shedding chunks, or deforming as it rolls, the prediction becomes much harder. Small changes early in the roll create wildly different outcomes at the bottom. Apophis is the snowball. The 2029 flyby is the top of the hill, and we don't know yet whether it will reach the bottom intact or transformed into something we didn't anticipate. There's another mechanism worth considering: outgassing. Some asteroids, particularly those that formed in the outer solar system and migrated inward, contain volatile materials, ices that can sublimate when heated. If Apophis has any buried volatiles, the tidal stress or frictional heating from material movement could trigger localized outgassing. Jets of gas escaping from the surface. It happened to comet 67P/Churyumov-Gerasimenko, creating dramatic plumes that change the comet's rotation. If Apophis outgasses, even slightly, that creates an additional force, a rocket effect, another term in the orbital equation that we didn't account for, another reason the post-flyby orbit might not match the predictions. The scenario tree here branches rapidly. Benign outcome: flyby happens, minor surface changes, orbit slightly perturbed but still safe. Moderate outcome: rotation, state changes, mass redistribution, Yarkovsky effect altered, long-term risk increases but remains manageable. Severe outcome: structural changes, mass loss, multiple fragments, chaotic post-flyby dynamics. Risk assessment restarts from scratch. We don't know which branch we're on. We won't know until it happens. And that uncertainty is, in many ways, more troubling than a simple binary of hits us, or doesn't hit us. Because uncertainty means we can't plan, can't prepare, can't allocate resources appropriately. The researchers modelling these scenarios aren't saying they're likely. They're saying they're possible. They're saying the physics allows for them. They're saying we need to be ready to respond if observations after the flyby suggest we're in one of the less benign branches. And here's the thing about asteroid impacts. The difference between a near miss and a civilization-ending event can come down to whether a rock that was barely holding together stayed intact or didn't, whether a surface landslide happened or didn't, whether the timing of the flyby aligned with a particular rotation state or didn't. Tiny contingencies, massive consequences. That's the universe we live in. Part 5. The futures. We're not talking about. Let's map out what April 13th, 2029 might actually mean for the decades that follow. Because this isn't just about one flyby. This is about trajectory, about the orbital space Apophis will occupy for the rest of this century and beyond. Right now, Apophis orbits the Sun with a period of roughly 0.9 years. It's what astronomers classify as an A10-class asteroid, meaning its orbit is smaller than Earth's, though it does cross our orbit periodically. After the 2029 flyby, that changes. Earth's gravity will alter Apophis's trajectory enough that its orbital period increases to around 1.2 years, according to projections from the European Space Agency. It will transition from a 10 to Apollo class, meaning its average distance from the Sun increases. That sounds like good news, right? The asteroid is being pushed into a larger orbit, farther from Earth on average. But orbital mechanics is rarely that simple. What matters isn't the average distance. What matters is the points where the orbits intersect, the nodes where Earth's path and Apophis's path cross each other in space, and those intersection points don't go away just because the asteroid's orbital period changed. In fact, depending on how the timing works out, the flyby could position Apophis such that future close approaches become more likely, not less. This is where the concept of gravitational keyholes becomes crucial. Imagine Earth's gravitational field in space as a landscape with hills and valleys. An asteroid passing through that landscape will have its trajectory bent. Most trajectories result in the asteroid flying past harmlessly, but there exist narrow regions, keyholes, where if the asteroid passes through exactly the right spot, Earth's gravity will bend its path such that it comes back on a collision course years or decades later. For Apophis, this was the whole story back in 2004. Initial observations suggested a small but real probability that Apophis would pass through a keyhole during the 2029 flyby, setting up an impact in 2036. That probability was calculated at 2.7% at one point, which in asteroid risk terms is absolutely terrifying. Further observations refined the orbit and ruled out that particular keyhole. But keyholes don't just disappear because we've ruled out one scenario. The gravitational landscape is full of them. They're typically only a few hundred meters to a few kilometers wide, tiny targets in the vastness of space. But Apophis will be passing through that landscape at close range, and we're still refining exactly where. The Monte Carlo simulations that researchers run to map out future risk look like probability fans. You start with the most likely trajectory, and then account for uncertainties. Each uncertain parameter gets varied within its measured range. You run thousands or millions of simulations, each with slightly different starting conditions, and you see where they end up. Most of those simulated Apophis asteroids fly away safely, but some small fraction, the tail of the distribution, end up in scenarios where future close encounters become concerning. Maybe not impacts, but close passes that require monitoring, and that fraction could grow if the post-flyby measurements reveal larger uncertainties than we currently assume. Before the flyby, Apophis's semi-major axis, the average radius of its orbit, is roughly 0.9 astronomical units. After the flyby, models suggest it increases past 1.1 astronomical units. That's a substantial change, equivalent to millions of kilometers in orbital circumference. It fundamentally reshapes when and where Apophis can come close to Earth again. The next few decades after 2029 become a question of resonance. Does Apophis end up in an orbital configuration where it returns to Earth's vicinity on a regular schedule, every 5 years, every 7, every 13? Resonances are stable, which means once locked in, they persist. If Apophis ends up in resonance with Earth, we'll be seeing it repeatedly. And each encounter is another chance for gravitational perturbations. Another roll of the dice. This is why the planetary defense community talks about the flyby as a pivot point. It's not just an event, it's a branching. Before the flyby, we're on one trajectory branch. After the flyby, we're on another. And which branch we end up on determines the risk landscape for our grandchildren. Let me be clear about what current data shows. The most likely scenario, the central expectation, is that Apophis flies by safely in 2029 and does not return as a threat within the next century. The models that NASA and the European Space Agency have published support this. The observations we have support this. The smart money is on everything being fine. But science isn't about the most likely scenario. Science is about understanding the full range of possibilities and their probabilities, and the tail scenarios, the low probability but high consequence outcomes, those are still on the table. They're still being researched. They're still keeping some scientists up at night. The stakes here aren't abstract. An Apophis impact wouldn't be an extinction event, but it would be catastrophic on a regional or continental scale depending on where it hit. Ocean impact, tsunamis that redraw coastlines, land impact, devastation comparable to thousands of nuclear weapons concentrated in one moment, millions of casualties, economic disruption that would dwarf any recent disaster. And that's assuming the asteroid hits intact. If structural changes during the flyby create multiple fragments on slightly different trajectories, you could have multiple impact sites, or you could have one large impact plus a shotgun blast of smaller pieces raining down over a wide area. This scenario tree includes branches we haven't even discussed yet. What about the satellite infrastructure Apophis will pass through? If the asteroid's gravity is strong enough, could it perturb satellite orbits? Could it trigger collisions in an already crowded orbital environment? These are second-order effects that barely anyone is modelling, but they're not impossible. We have a little over 3 years before the flyby. That's our window to measure everything we can about Apophis, to refine the models, to narrow the uncertainties, to prepare response options in case the post-flyby data shows something we didn't expect. 3 years to answer the question, are we actually safe, or are we just lucky so far? The answer matters more than most people realise. Part 6. The invisible push that changes everything. There's a force acting on Apophis right now that's weaker than a mosquito landing on your arm. A force so subtle that detecting it requires years of patient observation and sophisticated mathematical analysis. A force that, over decades, could mean the difference between a safe passage and a collision. It's called the Yarkovsky effect, and it's one of the most important things you've never heard of. The concept is elegant in its simplicity. Asteroids absorb sunlight. That energy heats the surface. The surface re-radiates that energy as infrared light, as heat radiation. But the asteroid is also rotating. So the warmest part of the surface, the part that was in full sunlight hours ago, has rotated away from the sun by the time it's hot enough to radiate most efficiently. When that hot surface faces away from the sun and releases its energy, the photons carry momentum. Those escaping photons push against the asteroid, creating a tiny thrust. For a stationary object, this wouldn't matter. The thrust would be symmetric. But a rotating asteroid develops an asymmetry. The afternoon side, if you will, radiates more than the morning side. The result is a net force that either speeds the asteroid up in its orbit or slows it down, depending on which way it's rotating. The numbers are absurd. We're talking about accelerations measured in fractions of a nanometer per second squared, a force roughly 10 to the negative 10th times weaker than Earth's surface gravity. You could replicate this force by breathing gently on a boulder, but apply that breath for 20 years and you've moved the boulder kilometers. Apply it for a century and you've moved it tens of thousands of kilometers. For Apophis, the Yarkovsky effect matters because we don't know its magnitude precisely. We have constraints. Radar observations combined with optical tracking over the past 2 decades have allowed researchers to estimate Apophis's size, shape and spin rate. Those measurements feed into thermal models that predict the Yarkovsky acceleration. Some papers have claimed marginal detections, others show null results or very tight constraints that suggest the effect is smaller than expected. The variation comes from uncertainties in parameters we can't directly observe, things like thermal inertia, how quickly the surface heats up and cools down, surface roughness, which affects how evenly heat is absorbed and radiated, composition, whether the surface is rocky, dusty, or some mixture. Now here's where the 2029 flyby becomes critical. Remember those tidal forces we discussed, the ones that might trigger surface changes? If the flyby alters Apophis's surface properties, the Yarkovsky effect changes. Fresh rock exposed from subsurface might have different thermal inertia. Dust redistribution might change albedo. Shape deformation might alter how sunlight hits the surface. And then there's the rotation complication. Current models assume Apophis is in a simple rotation state, spinning around a single principal axis like a well-thrown football. But what if it's not? What if Apophis is tumbling, rotating chaotically around multiple axes simultaneously? This isn't academic hair-splitting. Tumbling asteroids have been observed. The famous asteroid Tutati tumbles. It makes predicting their thermal behaviour exponentially harder, because the sun-heated surface is no longer predictable. One moment the equator is baking, the next moment a pole region is in full sun. The Yarkovsky thrust vector precesses, it wobbles. Trying to calculate the long-term orbital effect becomes an exercise in chaos theory. If the 2029 flyby nudges Apophis into a tumbling state, perhaps by changing its rotation rate or axis due to tidal torques, our ability to predict its future trajectory degrades significantly. The neat orbital projections that extend a century into the future suddenly have much wider error bars. Researchers have attempted to detect whether Apophis is already tumbling by analysing light curve data, the brightness variations as the asteroid rotates. The results are inconclusive. The data is consistent with simple rotation but doesn't rule out a slow tumble. We need better observations. This is where measurement error propagation becomes important. In orbital dynamics, small errors in initial conditions grow over time. It's a classic example of sensitive dependence on initial conditions. If your measurement of Apophis's current position is off by 1 kilometre, your prediction of where it will be in 5 years might be off by thousands of kilometres. Now add uncertain Yarkovsky acceleration on top of that. You're not just propagating position error, you're propagating acceleration error. The uncertainties compound. They multiply. By the time you're projecting decades ahead, the possible positions form a cloud rather than a point. That cloud is what risk assessors work with. They calculate the probability that any part of that cloud intersects Earth at some future date. Right now, those probabilities are tiny for Apophis. But if the cloud grows because post-flyby observations reveal larger Yarkovsky effects than expected, or because tumbling introduces chaotic dynamics, those probabilities increase. Think of it like a game of pool. You hit the cue ball and watch it strike another ball. If you know exactly how you hit the cue ball, exactly how fast it's moving, exactly where it will strike, you can predict where the other ball will end up. But introduce tiny uncertainties in any of those parameters, and your prediction becomes a probability distribution. The ball will probably end up in this general region, but it could end up elsewhere. Apophis is the ball. The Yarkovsky effect is one of the uncertain parameters, and we're trying to predict not just one collision, but a series of them stretching decades into the future. The modelling papers that keep appearing in the literature are attempting to narrow those uncertainties. They're exploring how different thermal inertia values change the Yarkovsky acceleration. They're simulating tumbling scenarios. They're calculating sensitivity coefficients that tell you which parameters matter most. What they're finding is that for Apophis, given its orbit and size, the Yarkovsky effect is probably significant enough to measure over the timescales we're concerned with. But probably isn't good enough for planetary defence. We need measurements precise enough that the uncertainties shrink to manageable levels. And that's why missions to Apophis aren't just scientific curiosity projects. They're risk mitigation. Every measurement we make, every parameter we constrain, every uncertainty we reduce, that shrinks the probability cloud. That gives us confidence we actually understand where this rock is going. Or conversely, it tells us we're in more trouble than we thought. Part 7. The Architecture of Chaos. When you picture an asteroid, you probably imagine something solid. A chunk of iron or stone tumbling through space, hard enough to survive the journey from the asteroid belt, strong enough to hold together under its own weight. For many asteroids, that picture is wrong. Dead wrong. The term of art is rubble pile. It sounds almost comical, like something a toddler builds with blocks. But it describes a real physical configuration that's both fascinating and terrifying. A rubble pile asteroid is a gravitationally bound aggregate, a collection of smaller rocks, ranging from house-sized boulders down to fine dust, all held together by mutual gravity and possibly weak cohesive forces. No structural strength in the traditional sense, just gravity and friction. The reason this matters for Apophis is that rubble piles respond to stress very differently than solid bodies. Apply force to a monolithic asteroid and it either withstands that force or fractures catastrophically. Apply the same force to a rubble pile and you get deformation, grain flow, internal reorganization. The structure adapts, shifts, settles into a new configuration. And tidal forces are exactly the kind of stress that can trigger this behavior. The 2023 Kim paper on tidal resurfacing took this seriously. They built models of Apophis as a rubble pile with various assumed internal properties: porosity, the fraction of empty space between grains; cohesion, how strongly the grains stick together; angle of repose, the maximum slope at which the material remains stable. Then they subjected those models to the tidal stress of the 2029 flyby. The results showed that even with conservative assumptions about cohesion, surface material movement was plausible. Slopes steeper than the angle of repose would fail. Material would slump downhill. The surface would rearrange itself in response to the tidal gradient. 1% doesn't sound like much until you visualize it. Apophis is roughly 340 meters across. 1% of its surface area is thousands of square meters. Picture a hillside the size of several football fields suddenly experiencing a landslide. Rock and dust sliding, exposing fresh material underneath, changing the local topography. Now scale up the what if. What if Apophis's internal structure is weaker than the conservative models assumed? What if the porosity is higher, meaning more void space and less structural integrity? What if the cohesion is lower, meaning the grains are barely clinging together even now? Laboratory experiments on meteorite samples have shown how fragile these materials can be. Take a chunk of carbonaceous chondrite, a primitive meteorite type that likely represents asteroid composition. Apply stress. Watch it crumble. The material has almost no tensile strength. It's held together by compression and friction, nothing more. If Apophis is made of similar material, the tidal forces during the flyby aren't just theoretical concerns. They're potential triggers for major structural changes. There's an analogy that works here. Think of a beanbag chair. Deform it and it adapts, squeeze it and it bulges elsewhere. The beans inside flow to accommodate the force. Now imagine that beanbag is 340 meters across and flying through a gravitational field so intense it creates differential forces across its diameter. The beans are going to move. For Apophis, moving beans means moving mass. Moving mass means changing the mass distribution. Changing the mass distribution means changing the moment. Of inertia, the resistance to rotational changes. That affects how the asteroid spins. Spin changes feed into thermal modelling. Thermal modelling feeds into Yarkovsky predictions. Everything is connected. There's another scenario that keeps appearing in the technical discussions, one that's more speculative but physically plausible. Internal grain flow. Not just surface slumping, but deep reorganization. If Apophis's interior is loosely packed, tidal forces could cause grains to shift and settle, like sand in an hourglass. The asteroid could literally compact itself during the flyby, becoming slightly smaller and denser. That would change the gravitational interaction with Earth. It would change the orbital deflection. It would change everything downstream from that moment. The porosity question is critical because we can't directly measure it from Earth. We can measure Apophis's size using radar. We can estimate its mass by observing how its gravity affects the orbits of any nearby objects, though Apophis doesn't have any known satellites to provide that measurement. Without independent mass and volume measurements, we can't calculate density. Without density, we can't constrain porosity. Without knowing porosity, we can't model internal structure. We're flying blind on one of the most important parameters. Some researchers have attempted to infer porosity by comparing Apophis to similar-sized asteroids that have been visited by spacecraft. Itokawa, a small asteroid visited by Japan's Hayabusa mission, turned out to be a rubble pile with roughly 40% porosity. Bennu, visited by NASA's OSIRIS-REx mission, also showed clear evidence of rubble pile structure. If Apophis is similar, we're looking at an object that's part rock, part void space. But what if it's not similar? What if Apophis is an outlier, either more solid or more fragile than the comparison cases? We're making assumptions based on limited data, and assumptions are where risk hides. The cohesion question is equally vexing. Some asteroids have surfaces dominated by fine regolith, dust that can develop weak cohesion through processes we don't fully understand. Electrostatic forces, maybe. Sintering from radiation exposure, maybe. Van der Waals forces between grains, maybe. The literature is full of maybes because we haven't directly measured cohesion on enough asteroids to have a clear picture. If Apophis has moderate cohesion, the tidal forces might not do much. The surface stays put. The structure remains intact. We breathe a sigh of relief. But if cohesion is weak, if the surface is barely held together even now, the flyby could trigger widespread changes. There's a darker possibility that appears in some modelling papers. Rotational breakup. If the flyby spins Apophis up, increases its rotation rate beyond a critical threshold, centrifugal forces could overcome gravity and cohesion. The asteroid could start shedding material from its equator. Or worse, it could split along structural weaknesses. This has happened. We've observed it. Asteroid P/2013 R3 was caught in the act of breaking apart, pieces slowly drifting away from the main body. The mechanism isn't fully understood, but probably involves spin-up from thermal effects or impacts. For Apophis, the question is whether the tidal torque during the flyby is large enough to spin the asteroid faster. The preliminary calculations suggest it's not, that the torque is too weak. But those calculations assume we know Apophis's current rotation rate and principal moments of inertia accurately. Do we? The answer is we think so, but there's uncertainty, and in that uncertainty lives risk. Imagine you're an engineer designing a bridge. You need to know the load-bearing capacity of every structural member. You test materials, run simulations, build safety margins. Now imagine someone tells you that one of the support columns might be hollow. Not definitely hollow, just maybe. How does that change your risk assessment? Apophis is the bridge, the 2029 flyby is the load test, and we're not entirely sure what the bridge is made of. Part 8. The keyhole that haunts us. Let me tell you a story about how close we came to a very different timeline. A timeline where billions of people spent years living under the shadow of an incoming asteroid, where planetary defense went from theoretical exercise to urgent necessity, where the question wasn't if we'd have to deflect an asteroid, but how. In December of 2004, astronomers at the Kitt Peak National Observatory picked up a new near-Earth asteroid. Object designation 2004 MN4. Routine observation, the kind that happens hundreds of times per year. Preliminary orbit calculations suggested nothing remarkable, just another small asteroid crossing Earth's orbit. Then they ran the numbers forward. The initial probability assessment for an impact in 2029 was roughly 1 in 40, 2.7%. Those aren't lottery odds, those are Russian roulette odds. For context, asteroid impacts are typically assessed using the Palermo Technical Impact Hazard Scale. Apophis briefly reached a level that had never been seen before for any object. The planetary defense community went into overdrive. The reason for that high probability wasn't that Apophis was definitely going to hit us. It was that the early orbital data had large uncertainties, and when you propagated those uncertainties forward to 2029, a concerning fraction of the probability distribution intersected Earth. More observations came in. The orbit was refined. The probability dropped. By late 2004, it was down to around 1 in 45. Better, but still terrifying. Then in 2005, archival images from 2004 were found, extending the observational arc. The orbit became more precise. The 2029 impact probability dropped to essentially zero. But something else emerged from that analysis, a keyhole scenario for 2036. Here's how keyholes work. When an asteroid passes close to Earth, our planet's gravity bends its trajectory. How much the trajectory bends depends on exactly where the asteroid passes. Most trajectories result in safe deflections. The asteroid flies by, gets nudged onto a slightly different orbit, and that's that. But there exist narrow regions in space, keyholes, where the deflection is just right to set up a future collision. Think of it as gravitational pinball. The asteroid is the ball, Earth is a bumper. Hit the bumper at the wrong angle and the ball bounces straight toward the next bumper, which happens to be Earth again several years later. For Apophis, the 2036 keyhole was a region roughly 600 meters wide that the asteroid would have to pass through during the 2029 flyby to set up a 2036 impact. 600 meters sounds large, but in the context of a close approach distance of 30,000 kilometers, it's a needle in a haystack. As observations continued through the 2000s, that keyhole was ruled out. The refined orbit showed Apophis would miss it by kilometers. The 2036 impact scenario evaporated. By 2021, enough additional data had accumulated that NASA and the European Space Agency officially declared Apophis posed no risk for at least a century. Case closed, right? Not quite. Because while that specific keyhole is no longer a threat, the gravitational landscape is full of them. The 2029 flyby will deflect Apophis through a region of space where other potential keyholes exist for encounters in the 2040s, 2050s, 2060s, and beyond. We haven't mapped all of them. We can't, not with current orbital uncertainties. What we can do is calculate the general probability that Apophis will pass through any keyhole leading to a future impact. With current data, that probability is very small, but it's not zero. And more importantly, it depends critically on measurements we haven't made yet. The geometry here is unforgiving. Before the 2029 flyby, Apophis orbits with a semi-major axis of about 0.9 astronomical units. After the flyby, models predict it increases to around 1.1 or 1.2 astronomical units, depending on the exact encounter geometry. That's a substantial change, equivalent to reshaping the entire orbit. The asteroid transitions from a 10 class to Apollo class. Its orbital period increases from 0.9 years to roughly 1.2 years. The timing of when it returns to Earth's vicinity shifts. The resonance relationships change. Resonance is the key word here. In orbital dynamics, resonance occurs when two objects have orbital periods that are simple integer ratios, like 2 to 3 or 5 to 7. When objects are in resonance, they encounter each other repeatedly at the same points in their orbits. The perturbations accumulate. What might be a tiny gravitational nudge in a single encounter becomes a significant effect over multiple encounters. If Apophis ends up in or near a resonance with Earth after the flyby, we're looking at repeated close approaches on a predictable schedule. Each approach is another chance for deflection, another roll of the dice, another opportunity for that gravitational pinball effect to either push us towards safety or toward danger. The Monte Carlo simulations that researchers run to assess long-term risk work by varying the input parameters within their uncertainty ranges and seeing where things end up. Current simulations using current orbital data and current assumptions about Yarkovsky effects and other perturbations show most outcomes are safe. Apophis flies by in 2029, gets deflected onto a new orbit, and doesn't return as a significant threat within a century. But those tails of the distribution, the low probability scenarios where things go differently, they're still there. And the width of those tails depends on how well we know the parameters. This is where post-flyby measurements become critical. If observations after April 13, 2029 show that Apophis's orbit is slightly different from what the models predicted, that means our models had errors. Those errors need to be corrected, and correcting them might mean the long-term risk assessment changes. Imagine a scenario. The flyby happens. Everything looks normal initially. But 6 months of tracking post-flyby reveals that Apophis's orbit is evolving slightly faster than expected. The Yarkovsky effect is stronger than the models assumed, maybe because surface changes altered thermal properties. Researchers recalculate the long-term projections with the new acceleration value, and they find a keyhole. Not for 2036, that's still ruled out, but for 2068 maybe, or 2093. A low probability, sure, maybe 1 in 1,000. Maybe 1 in 10,000, but not 0. Suddenly we're back to monitoring, back to refining the orbit, back to asking whether we need to consider a deflection mission just in case. This is the scenario that keeps planetary defense experts awake. Not the certainty of impact, but the possibility of living for decades under slowly evolving risk. The public can handle, we're safe, or even, we need to deflect this now. What's harder to communicate is, we think we're probably safe, but we need to keep watching, and we might need to do something eventually depending on how the data evolves. The difference between a hairline miss and a direct hit can come down to a velocity change of millimeters per second sustained over decades. That's the thickness of the line we're walking. That's how precise our understanding needs to be, and we're not there yet. Part 9, What? They're not telling you. There's a fascinating dynamic that plays out when space agencies communicate about asteroid risk. On one hand, they have a scientific obligation to be accurate. On the other hand, they have a public relations nightmare if they're too honest about uncertainties. Let's talk about March of 2021. That's when the European Space Agency officially removed Apophis from its risk list. NASA made similar statements around the same time. The messaging was clear and reassuring. No risk of impact in 2029. No risk for the foreseeable future. You can all sleep soundly. The scientific papers published around that same time tell a more nuanced story. They don't contradict the agency statements exactly, but they include caveats, discussions of remaining uncertainties, acknowledgements that future observations might change the assessment. The kind of hedging that's standard in scientific literature but doesn't make it into press releases. Why the discrepancy? Because institutions operate under different incentive structures than individual researchers. An agency like NASA or ESA has to balance scientific accuracy with public trust. Say too much about uncertainties and you risk panic. Say too little and you risk looking incompetent if something unexpected happens. There's also the mission planning angle. The European Space Agency is currently working on securing approval for the Ramses mission to Apophis. That approval depends on a Ministerial Council meeting in November of 2025. The mission's scientific case rests partly on the fact that the 2029 flyby is a unique opportunity to study tidal effects on an asteroid up close. But if the agency is simultaneously telling the public that Apophis poses significant risk, the mission becomes politically fraught. Is it a scientific mission or a defense mission? The optics get complicated. Similarly, NASA has redirected the OSIRIS-REx spacecraft, now renamed OSIRIS-APEX, to visit Apophis after the flyby. The scientific justification is sound. We need the measurements. We need to see what changed. But there's an unspoken subtext. We need to know if our models were wrong. Now let me be clear. I'm not suggesting conspiracy. I'm not claiming agencies are hiding imminent danger. What I'm suggesting is that institutional communication follows certain patterns, and understanding those patterns helps you read between the lines. When an agency says no significant risk, what they mean is no risk above our threshold for public notification given current data. That threshold exists for good reason. You don't alarm people over 1 in a million probabilities, but it also means that risks below the threshold don't get discussed in public communications even though they're still being actively researched. Look at the publication record. Papers on Apophis haven't stopped. Researchers are still modelling the Yarkovsky effect, still exploring tidal resurfacing, still calculating post-flyby orbital evolution. Why do that if the case is closed? Because in science, the case is never fully closed. There's always more precision to be gained, more parameters to constrain, more scenarios to explore. But that ongoing research doesn't make it into the headlines. The headlines were in 2021 when the risk list removal happened. The subtle refinements, the updated models, the narrowing of uncertainty bands that happens in preprint servers and peer-reviewed journals that most people never see. There's historical precedent for how these things unfold. In 2004, when Apophis was first discovered and the impact probability spiked, NASA held a press conference. They explained the situation. They noted that more observations would likely reduce the probability, which is exactly what happened. The communication was handled well, all things considered. But that was a case where the probability was high enough to warrant public notification. What about scenarios where the probability is low but non-zero, where the situation is ambiguous? Those don't get press conferences. They get cautious monitoring and internal discussion. Consider the funding cycles. Planetary defense missions require years of planning and budget allocation. If you're a mission planner at ESA or NASA, and you've identified a potential future risk scenario, even a low probability one, you need to start planning response options now, but you don't necessarily announce those plans publicly, because it could be misinterpreted as confirmation of danger. So what you get is this odd situation where agencies are simultaneously saying everything is fine in public while internally preparing missions, developing deflection concepts and refining risk models. Both statements are true in their context, but the optics are strange. There's also the international coordination angle. Planetary defense isn't a single nation problem. If Apophis posed real risk, the response would need to involve multiple space agencies, international treaties, resource sharing. Those discussions happen behind closed doors in working groups and committees that don't issue public transcripts. The United Nations has a framework for this, the Space Mission Planning Advisory Group, which coordinates international response to near-Earth object threats. They meet regularly, they discuss scenarios, and most of that discussion is not public-facing. Again, this isn't conspiracy. This is how complex international bureaucracies function. But it does mean that what you read in press releases represents the tip of an iceberg. The bulk of the analysis, the scenario planning, the what-if discussions, that happens out of public view. For Apophis specifically, I would bet that there are internal agency documents mapping out contingency plans for different post-flyby outcomes. If measurements show X, we do Y. If measurements show Z, we do W. Those contingencies don't represent predictions of what will happen. They represent due diligence. Be prepared for multiple scenarios. But if those documents existed and leaked, the headlines would write themselves. NASA has secret Apophis impact plans. Accurate in the sense that contingency planning is prudent. Misleading in the sense that contingency plans don't equal expected outcomes. This is the communication tightrope that agencies walk. Be honest enough that you maintain scientific credibility. Be reassuring enough that you don't cause unnecessary alarm. Be vague enough about uncertainties that you don't tie your hands if the data changes. For someone trying to understand the actual situation, the strategy is to read the primary literature. Not press releases, not news articles, the actual papers being published in journals like Icarus, Astronomy and Astrophysics, the Astronomical Journal. Read the abstracts, scan the conclusions. Look for phrases like requires further observation or uncertainties remain. That's where the real story lives. And what that literature shows is that while agencies are publicly confident, researchers are still actively working to nail down the parameters that determine long-term risk. The work continues because the uncertainties, while small, are not yet small enough to close the book completely. We'll know more after the flyby. The missions currently in development will provide measurements that collapse the uncertainty ranges. But until then, we're in a holding pattern, watching, calculating, and preparing for multiple possible futures, even while telling the public we're confident in one. Part 10. The Measurements That Matter. If you want to understand what we actually need to know about Apophis, forget the speculation for a moment and focus on the data gaps, the things we're uncertain about, the parameters that, if measured precisely, would tell us whether the 2029 flyby is genuinely safe or just probably safe. First and most important, mass. Sounds simple, right? Weigh the asteroid, except you can't just put it on a scale. The standard method for measuring asteroid mass is to observe its gravitational influence on another object. If the asteroid has a moon, perfect. Watch the moon's orbit, apply Kepler's laws, calculate the primary's mass. Apophis doesn't have a known moon. The alternative is to fly a spacecraft close to the asteroid and measure how the spacecraft's trajectory is perturbed by the asteroid's gravity. That's what missions like OSIRIS-APEX will do, but it requires getting very close and having very precise tracking of the spacecraft's position. The mass uncertainty translates directly into uncertainty about gravitational deflection during the 2029 flyby. Without precise mass, we can't precisely predict how much Earth's gravity will bend Apophis's trajectory. We can estimate based on size and assume density, but estimates have error, bars, and those error bars, when propagated forward decades, become kilometres or tens of kilometres of positional uncertainty. Second, rotation state. Is Apophis spinning simply around a single axis, or is it tumbling? If tumbling, what's the tumbling period and the orientation of the angular momentum vector? This matters for thermal modelling. A simply rotating asteroid has predictable sun illumination patterns. A tumbling asteroid does not. Current light curve observations, watching how the asteroid's brightness varies as it rotates, suggest simple rotation with a period of roughly 30.4 hours. But light curve data can be ambiguous. A tumbling asteroid with the right geometry can produce a light curve that looks like simple rotation. We need better data. We need spacecraft flybys with cameras that can watch the rotation directly. Third, shape and topography. Radar observations have given us coarse shape models, showing Apophis is elongated, somewhat peanut-shaped. But we need high-resolution topography. We need to know where the slopes are steep, where material might be unstable under tidal stress. We need to identify potential landslide sites before the flyby so we can predict what might change. The Ramses mission, if approved, will map Apophis at resolutions down to centimetres. That level of detail allows you to see boulders, identify regolith patches, assess surface roughness, all of which feeds into thermal models and structural models. Fourth, thermal inertia. This parameter describes how quickly the surface heats up in sunlight and cools down in shadow. High thermal inertia means the surface responds slowly, like rock. Low thermal inertia means it responds quickly, like dust. This is critical for calculating the Yarkovsky effect. We have estimates of Apophis's thermal inertia based on infrared observations, but the error bars are large. Factor of 2 or 3 uncertainty. That translates to similar uncertainty in predicted Yarkovsky acceleration. To narrow it down, we need spacecraft-based thermal imaging, measuring temperature variations across the surface under different illumination conditions. Fifth, albedo and surface composition. Albedo is reflectivity. How much sunlight does the surface reflect versus absorb? Composition tells you what minerals are present, which determines optical and thermal properties. Spectroscopic observations from Earth have given us hints that Apophis is an LL chondrite. a specific class of stony meteorite. But surface properties can vary across the asteroid. If the flyby exposes fresh material with different albedo, the thermal balance changes. The Yarkovsky effect changes. We need before and after measurements to detect any such changes. Sixth, regolith depth and cohesion. Is there a thick layer of loose dust on the surface, or is it mostly exposed bedrock? If there's regolith, how deep is it and how compacted? These questions determine how the surface will respond to tidal forces. Loose. Material will slump. Bedrock won't. The OSIRIS-REx mission to Bennu provided a dramatic example of why this matters. When the spacecraft touched down to collect samples, its sampling arm sank deep into the surface. The regolith was far less compacted than expected, almost fluffy. If Bennu had experienced strong tidal forces, that material would have flowed. We don't know yet whether Apophis is similar. Radar observations suggest a relatively smooth surface, which might indicate dust cover, but that's indirect evidence. We need contact measurements or very high-resolution imaging to assess regolith properties. Seventh, any active mass loss. Is Apophis currently losing material? Cometary activity, dust ejection, anything that would act as a non-gravitational force. Current observations show no evidence of activity, but the sensitivity limits are such that weak activity could be missed. Spacecraft flybys with dust detectors and cameras sensitive to faint emissions would nail this down. These 7 parameters are the critical ones. Get precise measurements of all 7 before the flyby, and we have a good baseline. Remeasure them all after the flyby, and we can quantify exactly what changed. The difference between before and after tells us whether our models are accurate. Now let's talk about the missions that will provide these measurements. OSIRIS-APEX, the redirected asteroid sample return spacecraft, will arrive at Apophis in April of 2029, about a month after the Earth flyby. It will spend 18 months in proximity, mapping the surface, measuring thermal properties, assessing any changes caused by the encounter. The Ramses mission, proposed by ESA and JAXA, would arrive at Apophis before the flyby. It would observe the asteroid in its pre-encounter state, monitor it during the close approach, and continue observations afterward. This before, during, after perspective is invaluable for understanding exactly what the flyby does to the asteroid. Both missions require approval and funding. OSIRIS-APEX is already in flight, so that's secured. Ramses faces a critical decision point at the ESA Ministerial Council meeting in November 2025. If approved, it would launch in 2028, arriving at Apophis in early 2029. There are also ground-based observation campaigns planned. Radar facilities like Arecibo collapsed in 2020. The Goldstone Solar System radar and the Green Bank telescope will observe Apophis during close approaches. The James Webb Space Telescope might contribute infrared observations. Amateur astronomers worldwide will track the asteroid's position and brightness. The point is, between now and 2029, Apophis will be one of the most intensively studied objects in the solar system. And immediately after the flyby, that intensity will increase. Every telescope that can point at it will do so. Every measurement we can make will be made. That data will answer the questions we have now. But it might also raise new questions we haven't thought of yet. That's how science works. You solve one puzzle and discover 3 more behind it. The ultimate goal is to shrink the uncertainty in Apophis's future trajectory to the point where we can say with confidence, not just high probability, that it poses no risk for a defined period. Currently we can say, no risk for a century, with confidence measured in percentages. We want to push that to higher percentages, tighter bounds, longer time spans, and if the measurements reveal something unexpected, if post-flyby observations show the orbit changed more than models predicted, then we recalculate, we revise, we potentially activate contingency plans. We prepare for the possibility that Apophis might return as a threat in future decades, and start planning deflection missions accordingly. This is planetary defense in action. Not dramatic last-minute heroics, but patient, methodical reduction of uncertainty. Measure, model, monitor, repeat, until we know enough to act, or to confidently decide that no action is needed. The clock is ticking. We have roughly 3 years before the flyby, and everything we learn in those 3 years will determine how we respond to what comes next. Part 11. When the Sun Strikes Back. On November 9th, 2025, just a few days ago, the sun erupted. A massive solar flare, X-class, the most powerful category we measure. The burst of radiation reached Earth 8 minutes later at light speed, ionizing the upper atmosphere, disrupting radio communications, triggering aurora visible as far south as mid-latitudes. But the electromagnetic radiation was just the opening act. 12 to 18 hours behind it came the coronal mass ejection, a billion-ton cloud of magnetized plasma travelling at hundreds of kilometers per second. When that hit Earth's magnetosphere, things got interesting. Geomagnetic storms at G4 severity, the second highest category. Satellites in low Earth orbit experienced increased drag from atmospheric expansion. GPS signals degraded. Power grid operators in high-latitude regions went on alert for potential transformer damage from induced currents. Communications with aircraft flying polar routes were disrupted. This is space weather. And while it makes for spectacular aurora photos, it also exposes a fragility in our technological infrastructure that most people don't think about until something breaks. Now connect this to Apophis. Not directly, the two phenomena are unrelated, but systemically they're very much related. Because our ability to track asteroids, to monitor their orbits with the precision needed for planetary defense, depends on a network of ground-based radar systems, optical telescopes, spacecraft, and satellites, all of which are vulnerable to space weather. Radar systems depend on radio wave propagation through the ionosphere. Solar storms distort the ionosphere, degrading radar performance. Optical telescopes can operate during storms, but if they're automated and rely on satellite timing signals for precise positioning, GPS degradation becomes a problem. Spacecraft can lose communications or experience anomalies when high-energy particles from solar events bombard their electronics. Imagine a scenario. April 13th, 2029. Apophis makes its close approach. Every telescope and radar system on Earth is pointed at it, trying to measure its post-flyby trajectory with maximum precision. And on that same day, the Sun launches a major coronal mass ejection directly at Earth. Suddenly, half your observational assets are degraded or offline. Radar tracking is unreliable. Satellite communications are intermittent. You're trying to make the most critical measurements in planetary defense history, while your instruments are being scrambled by forces completely beyond your control. This isn't hypothetical disaster mongering. Solar activity follows an 11-year cycle. The current cycle, cycle 25, peaked in 2023 but remains active. By 2029 we'll be in the declining phase, but that doesn't mean no activity. Major solar events can occur at any point in the cycle. The probability of a significant geomagnetic storm coinciding with the Apophis flyby is low, but it's not zero. And the consequences of that coincidence could be severe, not in terms of physical danger to Earth. The storm itself is manageable, but in terms of lost observational opportunities. There's a broader point here about systemic risk. Individual threats might be manageable, Apophis is being tracked, solar storms are monitored, we have contingency plans for both. But when multiple stresses hit simultaneously, systems can fail in unexpected ways. The technical term is common mode failure, a single event cascading through multiple systems because they share vulnerabilities. Our space-based infrastructure is more vulnerable than most people realize. There are thousands of active satellites in orbit. They provide communications, navigation, Earth observation, weather monitoring. They're the backbone of modern technology, and they're all exposed to space weather, orbital debris, and potential perturbations from close-passing asteroids. That last point is worth unpacking. When Apophis passes inside the geostationary belt, it will have its own tiny gravitational field. Could that field perturb satellite orbits? The calculations suggest no. Apophis is too small and moving too fast for its gravitational influence to matter for any satellite not in immediate proximity. But have those calculations been done with sufficient precision for every satellite in the region? The geostationary belt is crowded. Communications satellites, weather satellites, military assets, they're precisely positioned to remain above fixed points on Earth's equator. If one of them were nudged slightly off station, by an unexpected gravitational interaction or by operational issues during the global distraction of tracking Apophis, it could drift into another satellite's path. Collisions in geostationary orbit create debris that persists indefinitely. This is the nightmare scenario that space traffic management experts worry about. Not a single catastrophic event, but a cascade. One collision creates debris. Debris hits another satellite, more debris. Each impact exponentially increases the debris population until large swaths of orbital space become unusable. Kessler syndrome, named after the NASA scientist who first described it. Apophis won't cause Kessler syndrome, but a distracted satellite operations community dealing with the unprecedented event of a large asteroid passing through their orbital zone while simultaneously managing degraded communications from a solar storm that could lead to operational errors. Again, this is about systemic fragility. Our planetary defense capability isn't just about tracking rocks, it's about maintaining the technological infrastructure that enables that tracking. Radars need power, telescopes need communications, scientists need data links. All of it depends on a functioning, resilient system, and space weather is one of the primary threats to that system. Solar storms happen. We can predict them a few days in advance at best. We can't prevent them. We can only harden our infrastructure and have backup plans. So while the world fixates on the asteroid, the scientists planning the observational campaign for April 2029 are also thinking about space weather forecasts, backup communication channels, and what to do if primary tracking systems go offline at the worst possible moment. Because in the real world, threats don't wait their turn. They pile up, and sometimes the universe has a dark sense of timing. Part 12. When one telescope changes everything. In November of 2025, the James Webb Space Telescope delivered another revelation. Deep field observations of a galaxy at redshift 6.8, roughly 800 million years after the Big Bang, revealed spectral signatures of complex organic molecules. Polycyclic aromatic hydrocarbons, the kind of molecular structures that on Earth are associated with biological processes. The finding doesn't prove ancient alien life. It proves that chemistry capable of supporting life emerged very early in cosmic history. It rewrites assumptions about when and where the building blocks for biology appeared. The announcement rippled through the astronomy community. Social media exploded with speculation. And the broader public got a reminder of something important. Single instrument observations can flip entire fields overnight. JWST has been doing this repeatedly since it began operations. Galaxies that shouldn't exist according to models, forming too early and too massive. Stars forming in environments, thought inhospitable. Complex chemistry where we expected simple atoms. Every observation challenges previous assumptions. There's a parallel here to Apophis. We have models, we have predictions, we're reasonably confident, but we're also basing those models and predictions on limited observations from Earth. We've never had a spacecraft in close proximity to Apophis. We've never measured its properties directly. We've never watched it up close as it experiences tidal forces. What if, like JWST's surprises, the close-up reality of Apophis differs from our models in ways we didn't anticipate? What if some parameter we assumed was well constrained turns out to be wildly off? What if there's a physical process at work that we didn't include in the equations? The history of asteroid science is full of surprises. When the Galileo spacecraft flew by asteroid Gaspra in 1991, scientists expected a cratered, inert chunk of rock. They found grooves, fracture patterns, and a surface younger than expected. The asteroid had a geological history, processes that shaped it beyond simple impacts. When Near Shoemaker went into orbit around Eros in 2000, the detailed imaging revealed a surface covered in boulders the size of houses, sitting in fields of fine regolith. The dichotomy between massive rocks and dust raised questions about the asteroid's formation history that we're still working to answer. When Hayabusa reached Itokawa in 2005, the expectation was a small but solid object. Instead, the spacecraft found a rubble pile with distinct regions, smooth areas filled with fine particles adjacent to rough, boulder-strewn terrain. The asteroid looked like it had experienced catastrophic disruption and then reaccumulated from the fragments. When OSIRIS-REx touched Bennu in 2020, expecting a firm surface, the sampling arm sank deep into material with the consistency of a ball pit. The surface was so loosely consolidated that material billowed away during sample collection. Models had predicted moderate cohesion. Reality delivered near zero cohesion. Every close encounter with an asteroid has revealed something unexpected. Every spacecraft mission has forced us to revise assumptions. Why should Apophis be different? This is why the measurement campaign matters so much. It's not just about confirming what we think we know. It's about discovering what we don't know, about calibrating our models against reality rather than against other models. The JWST analogy works on another level too. When you build a more powerful instrument, you don't just see the things you were looking for more clearly. You see new things you weren't looking for at all. Phenomena that didn't appear in your predictions because you didn't know to predict them. Osiris, Apex and Ramses are our JWST for Apophis. They're orders of magnitude better than ground-based observations. They'll measure things we couldn't measure before. They'll see details we couldn't see before, and almost certainly they'll reveal surprises. The question is whether those surprises will be benign curiosities or game-changing discoveries that force us to recalculate risk. Consider thermal modelling. We build models of how asteroids heat and cool, how thermal energy drives the Yarkovsky effect. Those models are based on laboratory measurements of meteorite samples and theoretical calculations of heat transfer. They work reasonably well, explaining observed orbital evolution for several asteroids. But they're not perfect. Every model has free parameters that need to be calibrated. Surface roughness, for instance. A rough surface has more surface area exposed to sunlight than a smooth surface of the same overall shape. More surface area means more heating. But at what scale does roughness matter? Centimetre scale? Metre scale? We make assumptions, and those assumptions propagate through the calculations. What if close-up imaging of Apophis reveals surface roughness at scales we didn't account for? What if the thermal models need to be revised? Those revisions change Yarkovsky predictions, which change long-term orbital projections. Or consider rotation. We think Apophis rotates simply, but light curve observations from Earth have limited resolution. What if there's a slight wobble we haven't detected? What if the rotation axis isn't quite where we think it is? Small errors in rotation modelling create large errors in thermal modelling, because the sun illumination pattern depends critically on which part of the surface faces the sun at which time. This is the uncertainty space that spacecraft observations will collapse. We'll go from, we think the rotation period is 30.4 hours plus or minus a few minutes, to, we measured the rotation period to be 30.392 hours with precision of seconds. From we estimate the thermal inertias between 200 and 600 SI units, to we measured thermal inertia of 420 SI units in this region and 380 in that region. Precision collapses uncertainty. But it can also reveal discrepancies between model and reality, and those discrepancies are the doorways to surprise. The JWST organic molecules finding is a reminder that the universe doesn't always behave according to our expectations. Chemistry emerged earlier than we thought. Galaxies formed faster than we thought. Stars ignited in environments we thought were too hostile. Each surprise demanded explanation, which led to refined models, which will eventually be tested by new observations, which will likely yield new surprises. It's an iterative process. Observe, model, predict, observe again, revise. Science doesn't deal in absolute certainty. It deals in progressive refinement of uncertainty. For Apophis, we're approaching a major refinement event. The 2029 flyby and the spacecraft observation surrounding it will give us data quality unprecedented for this object. We'll learn more about Apophis in those months than we learned in the previous 2 decades of ground-based observation. And if history is any guide, we'll learn things we didn't expect to learn. Things that change the conversation. Things that open new questions even as they answer old ones. The optimistic interpretation is that spacecraft measurements will confirm our models are broadly correct, narrow the uncertainties to comfortable levels, and allow us to state with very high confidence that Apophis poses no long-term threat. Case closed with better data. The less comfortable interpretation is that measurements will reveal our models had blind spots, that some key parameter was misestimated, and that the long-term risk assessment needs to be recalculated from a more accurate starting point. Not necessarily higher risk, but different risk with different probabilities and timescales. We won't know which interpretation is correct until the data comes in. Until then, we're in the position of astronomers before JWST launched, confident in the models but aware that surprises are possible, even likely. The difference is that JWST's surprises are intellectually exciting but not existentially threatening. They change textbooks, not survival odds. Apophis surprises could be both. Intellectually exciting and also directly relevant to whether a 340-metre rock might someday be on a collision course with the only planet we can live on. That's why the missions matter. That's why the measurements can't wait. That's why, regardless of how confident we are in current safety assessments, we need to treat the next few years as a critical observation window that we cannot afford to squander. Because if there's one thing the history of space exploration has taught us, it's that nature doesn't care about our models. It just is, and our job is to understand it accurately enough to predict what it will do next. Part 13, Listening to Space-Time Ripple. On October 27th, 2025, the LIGO, Virgo, and CAGRA gravitational wave observatories announced the detection of another black hole merger. Two black holes, 40 and 50 solar masses respectively, spiralling together and colliding roughly 2 billion light-years away. The event lasted less than a second, but released energy equivalent to several solar masses converted entirely to gravitational radiation. This was the observatory network's 312th confirmed detection since observations began. The field has matured from first detection novelty in 2015 to routine survey operations. We're now mapping the population of black holes and neutron stars across cosmic history through the ripples they create in spacetime when they collide. But here's what's remarkable about gravitational wave astronomy from a methodological standpoint. The detections are incredibly indirect. LIGO measures changes in arm lengths of less than 1,000th of a proton's diameter. It's detecting motion smaller than subatomic scales in devices kilometers long. The signal is buried in noise from seismic activity, thermal fluctuations, quantum uncertainty in the mirrors themselves. Yet through sophisticated data analysis, template matching, and cross-correlation between multiple detectors, the signal emerges. What looked like noise resolves into physics, and that physics tells you the masses of the merging objects, their spins, their distance, even aspects of how matter behaves at nuclear densities. The success of gravitational wave astronomy is fundamentally about uncertainty reduction. The first detection in 2015 had large error bars on every parameter. The black holes were probably around 30 solar masses each, probably roughly 2 billion light-years away, probably not spinning rapidly. As more detections accumulated, as analysis techniques improved, as the detector network expanded, those uncertainties shrank. Now the field can measure black hole masses to a few % precision, can determine whether they're spinning and in what direction, can map out the distribution of masses and spins across the population, and use that to constrain formation theories. This is exactly the process needed for Apophis. Multiple observations over time, each adding information, each constraining parameters, each narrowing the uncertainty bands. Early observations in 2004 had huge error bars on the orbit. The asteroid could have been in a wide range of trajectories. As observations accumulated, the possible trajectories narrowed. Now we know the orbit precisely enough to predict the 2029 close approach geometry to within kilometers. But like gravitational wave detections, precision comes at a cost. It requires sustained observation campaigns. It requires multiple instruments cross-checking each other. It requires sophisticated modelling to extract signal from noise. And it requires time. That last point is crucial. Gravitational wave astronomy couldn't happen without years of technology development, detector upgrades, and observing runs. The knowledge built incrementally. Similarly, our understanding of Apophis has built incrementally over 2 decades of tracking. The difference is that gravitational wave astronomy can take its time. Discover one black hole merger this year, another next year, slowly build the population map. There's no deadline pressure. The black holes aren't going to hit us. Asteroid tracking has deadlines. If Apophis is going to pass through a keyhole that sets up a future impact, we need to know before that happens, not after. We need to measure the parameters that determine whether it passes through the keyhole while we still have time to do something about it if necessary. This is where the analogy to gravitational wave science becomes instructive. In that field, when a new data run begins, the collaboration has planned out exactly what sensitivity they need to achieve, what backgrounds they need to suppress, what systematic errors they need to control. They don't just turn on the detectors and hope for the best. They systematically optimize for the measurements that matter. The same principle applies to Apophis observation campaigns. We need to identify the critical parameters, the ones that contribute most to long-term uncertainty, and focus measurement efforts there. Mass is more important than surface color. Rotation state is more important than exact mineralogy. Thermal inertia is more important than whether there are small boulders versus large boulders. Prioritization matters because observational resources are limited. Telescope time is precious. Spacecraft missions are expensive. Radar campaigns require coordination across multiple facilities. You can't measure everything to arbitrary precision. You have to focus on the measurements that collapse uncertainty most efficiently. This is what mission planners are doing right now for OSIRIS, APEX and Ramses. They're building observation plans that maximize information gain. Which surfaces to image at high resolution, which regions to target for thermal measurements, how long to observe rotation to nail down the wobble, if any. Every decision is an optimization problem balancing science return against resource constraints. Gravitational wave astronomers talk about golden events, detections that are particularly information-rich. Maybe because the signal was loud, or because multiple detectors caught it with good geometry, or because electromagnetic counterparts were observed giving additional constraints. Those golden events disproportionately advance the field. The Apophis flyby is a golden event for planetary defense. It's a once-in-a-millennium opportunity to observe tidal effects on a large asteroid at close range, to measure before and after states with spacecraft-level precision, to watch the solar system perform an experiment that we could never perform ourselves. Missing that opportunity would be unconscionable. It would be like having LIGO operational but turned off during a nearby supernova, or having JWST but pointing it away from the most distant galaxies. You don't squander golden events. That's why the scientific community is pushing hard for mission approval and funding. That's why observation campaigns are being planned years in advance. That's why international cooperation is being emphasized, getting as many instruments and facilities involved as possible. Because unlike gravitational wave astronomy, where you get hundreds of events to learn from, we get one Apophis flyby, one chance to make the measurements that matter, one opportunity to validate or revise our models before the next critical decision point decades down the line. The gravitational wave comparison also highlights something else. Uncertainty is not the enemy. Uncertainty is simply lack of information, and information can be gained through observation. The question is whether you make the observations in time. For black holes billions of light years away, in time is flexible. For an asteroid passing 30,000 kilometers from Earth, in less than 3.5 years, in time has a deadline, and that deadline is approaching whether we're ready or not. Part 14. When Machines Learn Chaos. In 2025, artificial intelligence crossed another threshold. Large language models achieved capabilities that, a few years prior, would have seemed like science fiction. Image generators created photorealistic scenes from text descriptions. Protein folding, once a grand challenge problem, became routine. AI systems began contributing to scientific research not just as tools but as co-authors, identifying patterns in data that human researchers might have missed. This revolution has reached astrophysics. Machine learning algorithms now process data from surveys like the Zwicky Transient Facility, identifying asteroids, detecting supernovae, classifying galaxies. AI-driven orbit determination can take sparse observations and predict trajectories faster than traditional methods. Neural networks trained on synthetic data can identify subtle periodicities in light curves that might indicate binary asteroids or complex rotation states. For Apophis, AI tools are being deployed to extract maximum information from limited observations. Algorithms that can denoise radar data, enhancing weak returns to reveal surface details, machine learning models that can predict how tidal forces will reshape the asteroid based on simulations of various internal structures, neural networks trained to recognize mass shedding signatures in optical tracking data. This is powerful, but it also introduces new categories of risk. Model risk. The danger that your AI system is wrong in ways you don't understand because the decision-making process is opaque. Here's the problem. Traditional orbital dynamics is transparent. You write down equations of motion, you specify initial conditions, you numerically integrate. If your prediction is wrong, you can trace back through the calculation and identify where the error came from. Was it the initial position, the mass estimate, the acceleration model? Transparent processes are debuggable. Machine learning is often not transparent. A neural network trained on thousands of simulated asteroid encounters might learn to predict post-flyby orbits with impressive accuracy on the training set. But what is it actually learning? What features is it using? If it makes a wrong prediction for Apophis, can you figure out why? This is the black box problem. AI systems can be incredibly effective pattern matchers, but they can also fail in unexpected ways when confronted with data outside their training distribution. An algorithm trained on simulated rubble pile asteroids might perform poorly on a monolithic asteroid without giving any indication that it's out of distribution. There's a famous example from medical AI. A machine learning system was trained to identify pneumonia in chest X-rays. It achieved impressive accuracy on the test set, apparently learning to recognize the subtle patterns radiologists use. Then someone dug into what the network was actually doing. Turned out it was keying off the presence of medical equipment in the image. If a patient was sick enough to need portable X-ray equipment brought to their bedside, that equipment appeared in the image, and the AI learned to associate those artifacts with pneumonia. It wasn't learning medicine. It was learning correlations that happened to work in the training data. For asteroid orbit prediction, similar failure modes could exist. An AI trained on synthetic data might learn to key off features that correlate with outcome in simulations, but don't exist in the real world. Or it might fail to account for physical processes that weren't included in the training simulations. The responsible use of AI in planetary defense requires validation against ground truth. For orbit prediction, that means comparing AI predictions to later observations of real asteroids to confirm accuracy. For Apophis, we won't have that ground truth until after the flyby. This creates a dilemma. Do you trust AI predictions made before the flyby, knowing they might have blind spots? Or do you stick with traditional methods that are transparent but potentially miss patterns that AI could catch? The answer, in practice, is both. Use AI tools to explore the data and generate hypotheses. Use traditional methods to verify and cross-check. Never rely solely on a black box prediction for decisions with high consequences. But there's a subtler issue. As AI becomes more capable, there's a temptation to let it do more of the thinking, to offload cognition to machines that can process more data than humans, run more simulations, explore more parameter space. That offloading is valuable, but it also creates dependency. What happens if the AI misses something subtle? What happens if there's a physical process at work in Apophis that wasn't in the training data because we've never observed it before? The AI won't flag it. It will confidently produce predictions based on patterns it knows, and those predictions will be wrong in ways that might not become apparent until too late. This is why domain expertise remains critical. Human scientists who understand the physics, who can look at AI outputs and ask, does this make sense? Who can recognize when predictions violate physical principles or seem inconsistent with other data. AI augments human capability but doesn't replace human judgment. For Apophis, the cutting edge involves hybrid approaches. AI pre-processing of data to extract weak signals, traditional dynamical modelling to ensure physical consistency, machine learning to explore parameter space efficiently, human interpretation to synthesize results and assess credibility. It's a powerful combination when done right, but it requires careful validation, cross-checking, and a healthy skepticism about overconfident predictions from any source, human or machine. There's also the adversarial angle. As AI becomes more capable, the potential for malicious use increases. Could someone train a model on asteroid data, identify vulnerabilities in tracking systems or prediction algorithms, and exploit those vulnerabilities to spread misinformation about impact risk? Could an AI be used to generate plausible but fake observations, poisoning databases that orbit determination relies on? These aren't immediate threats, but they're worth considering as the technology matures. Planetary defense depends on data integrity. If the data is compromised, the predictions are compromised. Ensuring that asteroid tracking systems are robust against manipulation is part of the broader challenge. The deeper point is that our understanding of Apophis exists in a socio-technical system. It's not just physics and data. It's also algorithms, software, institutional processes, communication channels, all of which can fail in ways that pure physics doesn't account for. An asteroid impact is a physics problem. But predicting and preventing that impact is a human problem, a technological problem, an institutional problem. The capabilities we bring to bear, whether radar or AI or spacecraft or international coordination, those capabilities have their own failure modes. Being aware of those failure modes is part of being prepared, not just preparing for the asteroid, but preparing for the ways our preparation might fall short, for the blind spots in our models, the biases in our data, the assumptions in our algorithms. Because the universe is not obliged to behave according to our best models. It just does what it does, and our job is to understand it well enough, despite our limited tools and imperfect knowledge, to predict what comes next and respond appropriately. For Apophis, that means using every tool available, AI included, while remaining cognizant of each tool's limitations. It means building redundancy into our observation system so no single point of failure can blind us. It means fostering the expertise to interpret complex data and make sound judgments under uncertainty. The machines can help, but they can't do it alone, and recognizing that limitation is as important as recognizing their capability. Part 15. The vigil we must keep. So let's bring this all back together. Let's talk about what actually matters as we approach April 13th, 2029, and the decades that follow. Apophis, the god of chaos, is coming. Not as an immediate threat, current data strongly suggests we're safe from impact in 2029, but as a test of our understanding, our observational capabilities, our modelling accuracy, our preparedness. The asteroid will pass within 30,000 kilometres of Earth's surface, closer than some satellites, visible to the naked eye in parts of the world, an event that will dominate news cycles for a day or two and then fade from public consciousness as people return to their daily concerns. But for the planetary defence community, the flyby is anything but routine. It's the moment when subtle forces, tiny accelerations, barely detectable changes could reshape the long-term risk landscape. It's when we find out whether 2 decades of careful observation and modelling were sufficient, or whether we're about to discover that nature has surprises we didn't anticipate. The Yarkovsky effect, that gentle photon pressure pushing asteroids over decades. The tidal forces that could reshape Apophis's surface, exposing fresh rock or triggering landslides. The rotation changes that could send the asteroid tumbling, complicating every downstream prediction. The possibility, however remote, of fragmentation or mass loss creating new hazards we'd have to track. All of these are real physical processes grounded in solid science. All of them have uncertainties large enough that precise long-term predictions remain challenging, and all of them will be tested during the 2029 encounter. The measurements matter: mass, rotation, shape, thermal properties, surface composition, structural strength. Each parameter we measure precisely is one we don't have to guess at. Each uncertainty we reduce shrinks the probability cloud of future positions, giving us clearer sight lines into what the next century holds. 2 missions stand ready to provide those measurements. OSIRIS Apex, already in flight, will arrive shortly after the flyby to document the aftermath. Ramses, pending approval, would observe before, during, and after, giving us the complete picture of how Earth's gravity transforms the asteroid. Ground-based campaigns will contribute. Radar will bounce signals off the spinning rock. Optical telescopes will track its position against background stars. Infrared instruments will measure its heat signature. Every observation adds information. Every data point constrains the models. But we also need to acknowledge the limits of our knowledge. The scenarios where structural changes are more dramatic than expected. The possibilities that our thermal models have blind spots. The chance that post-flyby measurements reveal errors in our pre-flyby assumptions, forcing a recalculation of risk. Those aren't reasons for panic, they're reasons for vigilance. They're why probably safe isn't the same as definitely safe, and why the work continues even after agencies have issued reassuring statements. The institutional dynamics matter too, how space agencies communicate about uncertain risk, how mission funding gets allocated amid competing priorities, how international cooperation functions when dealing with a global-scale threat. These aren't just administrative details, they're part of the infrastructure that planetary defence depends on. So are the systems we often take for granted. Satellites that provide communications and navigation. Power grids that keep telescopes and data centres running. The internet that lets researchers worldwide share data instantly. All of these have vulnerabilities, whether to solar storms or to simple failures, and those vulnerabilities could become critical during an observational campaign that we can't afford to mess up. The broader scientific lessons apply here too. How JWST keeps surprising us with observations that challenge assumptions. How gravitational wave astronomy progressed from first detection to routine survey through systematic refinement of instruments and techniques. How AI offers powerful tools but also introduces new failure modes that require careful management. Apophis is a reminder that we live in a solar system that's still dynamically active. Asteroids cross our orbit regularly. Most are small, burning up harmlessly in the atmosphere. Some are larger, capable of regional or worse devastation if they hit. And a handful, like Apophis, are large enough and on orbits that bring them close enough that we need to pay attention. The good news is we are paying attention. Asteroid discovery and tracking have improved dramatically over the past few decades. We now catalogue 95% of the near-Earth asteroids larger than 1 kilometre. We're working to extend that completeness to smaller sizes. Planetary defence has gone from science fiction to real programs with real budgets and real missions. But attention must be sustained. It's not enough to track an asteroid once and assume the orbit is known forever. Observations need to continue, models need to be updated, missions need to be flown. The work is ongoing, and it needs to remain ongoing. For Apophis specifically, the next 3 years are critical. The mission approvals that need to happen in 2025, the observation campaigns that need to be planned and executed before the flyby, the data analysis infrastructure that needs to be ready to process the flood of measurements that will come after April 13th, 2029, and then the follow-up, the years and decades of tracking Apophis in its new orbit, comparing predictions to observations, refining models based on what we learn, potentially preparing deflection missions if the data shows they're needed, though current assessments suggest they're not. This is the boring, unglamorous reality of planetary defence, not dramatic Hollywood countdowns and heroic last-minute interventions, but patient, careful, incremental work, observation, modelling, measurement, refinement, year after year, building the understanding that lets us confidently say we know what this rock will do, or finding out we don't know and adapting accordingly. The 3 policy steps that matter most are straightforward. Full funding for the Ramses and Osiris Apex missions. Those spacecraft are our eyes and hands at Apophis, and losing either one means losing critical data, open data sharing among all nations tracking the asteroid. The more eyes on the problem, the better the constraints, the faster we detect anomalies, and contingency planning for deflection missions, not because we expect to need them, but because if the data after 2029 changes the risk picture, we'll want response options ready. Beyond policy, there's a role for public engagement. When Apophis makes its close pass in 2029, it will be visible. People will watch. That's an opportunity to communicate what planetary defence is, why it matters, how science protects us from low probability but high consequence threats. Done well, that communication builds support for continued funding, for international cooperation, for the long-term perspective required to do this right. Done poorly, it either causes unnecessary alarm or fails to convey why the work matters. So as we count down to April 13th, 2029, 3 years and some months from now, the message is this. We're not facing imminent doom. Current data and models strongly suggest Apophis will fly by safely, but we're facing a critical juncture, a moment when small details could matter enormously for the long-term future. We need to approach that moment with the seriousness it deserves, with the best measurements we can make, with humility about what we don't know, with preparedness to respond if surprises emerge, and with the commitment to keep watching, keep modelling, keep refining our understanding for as long as Apophis remains an object of interest. That might be decades, it might be a century. But for as long as there's uncertainty, there's work to do. And for as long as there's work to do, we need people doing it. Scientists, engineers, mission planners, funding agencies, international partners. The whole ecosystem that makes planetary defence possible. The god of chaos is coming. We've known about it for over 20 years. We've been preparing. We've been measuring. We've been modelling. And when April 13th, 2029 arrives, we'll be watching. Not because we expect catastrophe, but because we respect the possibility. Because we know the universe doesn't care about our assumptions. Because we understand that small uncertainties today can become large consequences tomorrow. And because we're the species that learn to look up, to track the sky, to calculate orbits, and to ask, what if? That ability to plan, to prepare, to think beyond the immediate, that's what makes us different. That's what gives us a chance against threats that our ancestors could only attribute to angry gods. We're not perfect. Our knowledge has gaps, our tools have limitations, our institutions are imperfect, but we're trying. And sometimes, trying carefully and consistently over decades is enough. For Apophis, it has to be. Because unlike a distant interstellar, visitor that poses no threat, Unlike cosmic events billions of light years away that we can study at leisure, this one is close. This one is soon. This one matters. And while everyone's watching 3i Atlas drift through the outer solar system, the real story is happening right here, right now, in the observations being made tonight, in the missions being planned for 2028, in the calculations being refined this week. The god of chaos approaches, and when it arrives, we'll know whether we understood it well enough, whether we measured carefully enough, whether we were prepared. I hope we were. I think we were. But I'm watching the data just in case. Because in the end, hope is not a planetary defense strategy. Knowledge is. Preparation is. Vigilance is. And that vigil must continue until we know, with certainty beyond reasonable doubt, where Apophis will be not just in 2029, but in 2036 and 2068 and 2093, and every future encounter for as long as we or our descendants need to know. That's the work. That's the commitment. That's what it means to take planetary defense seriously in an age where we finally have the capability to do something about it. The countdown has begun. 3 years and counting. Let's make sure we use them wisely.